Hey, what's up? It's your old pal, Mr. Cook, and we are going to go through, I guess, this whole page. We'll do 20 and 21 and 22 and 23. And we can probably get through that in a decent amount of time. Okay, let's take a look. 20. The rate at which a population of predators in the forest grows over time is given by dp over dt is equal to 2, well, whatever, all that stuff. Where t is in months. If there are 30 predators in the forest at t equals 6 months, how many predators are in the forest at 12 months? So this is like the growth rate for the predators, dp over dt. So that means that if I were to take like the antiderivative of this thing, I would get the population of the predators, so p of t. So this second part, the second sentence where it says there are 30 predators in the forest at t equals 6 months, that just means that p of 6 months is equal to 30 predators. And then this one, it's saying how many predators are there when t is equal to 12. So in other words, that's like what we're looking for, p of 12. So how do capital P and dp dt relate to each other? Well, capital P is the antiderivative of P. So if we do an integral over the span from 6 to 12, we should be able to figure this out. So here's how we're going to do it. We're going to take, we're going to use the fundamental theorem of calculus, because basically, like, if I go from a to b of that integral function, that derivative function, p prime of t, in other words, dp dt, and then do dt, that's going to be equal to, if I take the antiderivative of p prime of t, it would just be p, so it would be p of b minus p of a. So, like, that's what I'm going to do. I'm just going to evaluate it strategically so that I can solve for something. So, like, if I go from 6 to 12 on this integral, so 6 here and 12 here, and 12 would be here, the 6 would be here, and I know this value, p of 6 is 30. I need to find that value, p of 12. So, this would be another one of those start plus accumulation method problems, okay? So that's what we're going to do, and that's the game plan, and that's how we're going to work through it. So let's start plugging some of this stuff in. The derivative function for the population is given to us, 2 e to the t plus 3t. And that's a pretty easy antiderivative to take. And then I know that p of 6 is 30. So now we add that start value over. So 30 plus integral 6 to 12, 2 e to the t plus 3t dt is equal to p of 12. So now we just got to figure out this part. So let's do that. All right, let's see. Or let me move this part over here, so we can just kind of keep moving forward with it. All right, so we get 30 plus, and then we're going to take the antiderivative of dp dt. So antiderivative of 2e to the t is still 2e to the t. Antiderivative of 3t would be 3 halves t squared. And then remember, since this is a definite integral, we don't need the plus c part, the plus constant part. So we're just going to do our fundamental theorem of calculus here for 6 and 12. All right, so that's the last part. I just got to plug those numbers in. And here's what I get. So I get 30 plus, and then if I plug in 12, it's going to be 2 e to the 12th plus 3 halves, 12 squared. And then minus, now I'm going to plug in 6. So I'm going to put parentheses around it because I need to subtract the whole thing. 2 e to the 6th power plus 3 over 2, 6 to the 2nd power. And then, that's my answer. Okay, so I'll just like put a little square brackets around it, or rectangular brackets. And this is how many predators are there going to be? It's that number, whatever it is, and then I'll write predators for the units. Okay, there we go. And you'd probably want to round up to the next number, but we don't have our calculators to calculate like e to the 12th and e to the 6th and stuff. So that's like good enough. You might want to make a comment. If you have to do something like this, you'd want to like say round into the net, round down to the nearest predator. So round it down to nearest predator, or nearest whole number. You want to round down because you wouldn't want to count like 0.5 of a predator or 0.3 of a predator. Like kind of a little bit morbid to think about. Oh yeah, it's like a leg and a tail or something like that. I don't know. All right, 21 and 22. We've got some summations, and we just need to write them up as definite integrals. This is just like kind of, it doesn't require much. It's just kind of figuring out like what parts go where, and that's it. So this is going to turn into a definite integral. So here's how a definite integral looks. It's going to be integral symbol, a starting value, an ending value, a function, and then like d times some variable, okay? And we'll just make up our variable, say it's x, so dx on there. Okay, so what values do we start with? What values do we end with? What's our function going to be? So the way that I teach it in class is that, like, in the summation notation that you have, you're always going to have like a sequence, and something's going to happen to that sequence. In this case, the sequence is squared. So that action of squaring it is going to be the function that you're dealing with. The sequence represents like the x values that you're going to be plugging in. So it's like the x value squared. So you just write x squared there. And then to find the beginning value, you, again, just look at your sequence, because that represents the x values. And this 3 over here tells you like where the integral is going to start. Technically, like what's happening here with the sequence is if you've got like, along your x-axis, if you have 3 plus some value, right, it means that you're starting at 3, okay? And then what you're doing is adding on a different number to get to the next x value. So like, the first x value would be 3 plus 5, 5 over n, so it'd be like over here somewhere. And then if I did 3 plus 10 over n, that would take this same distance, which is 5 over n, and I'd add on another one. Another 5 over n added onto it would be 3 plus 10 over n, which would be like the next value after that, this one here. See, it just keeps like moving the intervals over. That's what the sequence does. It just represents the x value, okay? You don't need to know that for this problem at all. You don't need to graph this out. You just need to identify the parts that lead you to this definite integral. So, once again, the sequence represents the x values, and whatever is happening to the sequence, that's like the basis for your function. So x squared is what we have. 3 is where we start our interval, because that's where all the x values start, so 3. And then after that, what you do is like, you can see how much it keeps changing, like those subintervals. That's going to tell you like, the difference. So what I usually do is I just look over here. That represents like the delta x on it, like, so how much it's going to change. And then this tells you how many intervals that you're going to have. In this case, it's going to be up to like infinity, like a lot of them. But that 5 right there, that tells you the difference from this lower number here to this upper number over here. So all you got to do is just add 5 onto that lower value. So if I do 3 plus 5, that gives me the endpoint of my interval 8, okay? So the key things to note are again, this, like what's happening to the sequence, that's your function. What value is adding, in your sequence, like what constant is being added on, that's your beginning value of your interval. And then how much change is going on, from your delta x. That's going to tell you where your endpoint is going to be on the interval. So if we put all that to the test here, here's the definite integral that we end up with. So integral, and then let's see, we need a starting point for our interval, ending point, a function, and then dx. I'll tell you also, the most missed part of this, from what I've seen over the past couple of years, is kids forgetting to like add on the dx part of it. So don't forget that, okay? It's worth a point just to have dx, because otherwise it's an incomplete definite integral. So make sure that you add that part in. Anyways, so here's our sequence, okay? So what's happening to the sequence? Well, it's the sine of the sequence. So that means that our function is going to be sine of x. What constant is being added on in our sequence each time? Well, before it was 3, so there's no number here. So if there's no number visible, what number is constantly being added on? 0. Okay, so 0 is going to be like in there. So just imagine this is like 0 plus 2 over n. That's 0 plus 4 over n, and so on. Okay. And then the difference between the lower bound and the upper bound is always going to be found with the delta x. So we're going to use that. So we add on 2 to 0, and that's going to be 2. So this is our completed definite integral. And that's number 22. Now 23 has to do with properties of integrals. The ones that you really want to know are how to split up an integral. So like if you had, like say, going from a to b, or whatever. Let's make up some numbers like 5 to 10 or something, okay, of some function f of x dx, then you'd want to know this property. You can split it apart with any arbitrary value in between. So if I know that like in between 5 and 10 there's like 7, for example, okay, then what I could do is I can split this up from 5 to 7 f of x dx, and then I just add on 7 to 10. So as long as I like complete the full interval, so going from 5 to 7 and then 7 to 10, these areas are going to be the same. So what it comes from is, imagine that you've got like some function, okay? And then you want your integral to start here and end here. Well, remember, it's the area under the curve. So this is like the area that's under the curve, right? But if I split it up somewhere, okay, so I have two integrals, like maybe this is one integral, and then this is my other integral. Do you see that like it finds these two separate areas? And if I take this area and then add on this area, it still gives me the total area, right? That's the idea behind this property. Okay, so that property is a good one to know. Another one to know is, multiples of stuff. So like if I have the integral from, of 2 of f of x or something like that dx, for some bound, maybe 5 to 10 again, then what I can do is I can just multiply 2 onto that integral. I can move constants out front if I wanted to, including subtraction signs and all that stuff. Any constant multiple you can move out front. And then the last one that I want to know is, it's like a really easy one. If you have like an integral and it starts and ends at the same spot, so maybe instead of 5 to 10, it goes from 5 to 5, that's always going to be equal to 0 every single time. And the reason for that is if the definite integral monitors like the area that's under the curve, if I have some function and I just have like one value, the width on this technically is 0, right? So the area that's under the curve, would be 0. That's the idea behind it. So know these three properties, and that'll serve you really well. Okay, so how does that work over here? Oh, sorry, I'm forgetting one, aren't I? I forgot the negation one. So if you negate an integral, so let's again use 5 to 10, f of x dx. This is the same as saying, like, if I were to pull a negative out of this, that same area, I would just reverse the orientation of the interval, I'm sorry. So I'd start at 10 and go to 5. That's all. So, you can negate the integral by just swapping the endpoints on the interval itself. And that's why this one's pretty helpful, because, if I want to find f of x dx from 12 to 7, that would be the same thing as saying, the integral from 7 to 12 and then negative of f of x. But I don't have a 7 to 12 on this. So what I'm going to do is attempt to find it, okay? So I do have f of x from 2 to 12, and I do have f of x from 2 to 7. So, I can use this rule over here and split the integral apart. So the integral from 2 to 12 of f of x dx is equal to the integral from 2 to 7 of f of x dx plus the integral from 7 to 12 of f of x dx. And I have number values for all of those. Like the area from 2 to 12 is given to me. It's 20. So I'm just going to erase that and put in the 20 there. And then I also know that the area from 7 to 12 is 6. Sorry, from 2 to 7 is 6. So I'm going to put a 6 right there. So if I want to find the area from 7 to 12, all I'd have to do is subtract 6 from both sides. So that tells me that that's equal to 14. If that's equal to 14, then that means that if I want to know what the area from 12 to 7 is, all I'd have to do is just negate the value that I just got. So that's going to be negative 14. Okay, so there you go. That's using the properties to solve it. Now, B is a little bit more complicated, but just by a little bit. So let's split this apart first. So this is the same thing as saying the integral from 7 to 12 of 2g of x dx minus the integral of 3 f of x over the same boundary from 7 to 12 dx again. Okay, and then constants can move out front. So I'm going to move that constant out front, 2. I'll move that constant out front, 3. All right, and then let's see. So g of x dx from 7 to 12, is that given to us? It is. Yeah, g of x dx from 7 to 12 is 5. So that means that this part just becomes 5. And then I just found out what f of x dx is from 7 to 12, the area under the curve from 7 to 12, it's 14. So this part just becomes a 14. And then, that gives you some number, and you can just leave it like that if you want. You don't need to figure out necessarily what it is. Okay, so that's number 23, using all these properties. I'm telling you, if you know these 4 properties, you'll do pretty well on this part of it if it shows up on the test. All right, I think we've got 2 more problems left. I'll save that for the last video. All right, So that's the end of this one. See you on the next one. Bye-bye.